So now we are honored to have Professor Bethany Ehlmann. Dr. Ehlmann is a professor of planetary science at Caltech, and she is going to be talking about Lunar Trailblazer. Bethany, please.
Okay, thank you very much, Greg, and the organizers. Can I confirm that you can both hear me as well as see my slides in presentation mode?
Yes, thank you.
Okay, fabulous. Well, I'm honored to, as principal investigator of Lunar Trailblazer, I'm honored to present at this forum following on the legacy of the LRO orbiter. We will be a small satellite for lunar water and lunar geology. And on behalf of my team, I am thrilled to tell you a little bit more about our mission and our progress. We are a confirmed NASA simplex mission. It's a Class D mission. And you can see the beautiful rendering of our Lunar Trailblazer spacecraft here made by Lockheed Martin. We travel to the moon as a rideshare mission on an ESPA Grande ring, and you can see solar panels folded up, comfortably nestled here in the ESPA volume. We travel to the moon using a hydrazine chemical propulsion system and insert into a 100-kilometer polar lunar orbit, where for over a year we'll do science mapping of the moon with our two instruments that are sensing reflected visible and shortwave infrared light and emitted thermal radiation from the moon. The flight system is on track for delivery in October of 2022, and we launch on the IMAP mission. I'm the PI, Rachel Klima at APL is the deputy PI. Our project management is at JPL. Lockheed Martin, as I said, is making our flight system. And then you see our two beautiful instruments, an imaging spectrometer that gets 50 to 90 meters per pixel in over 100 channels of light to sense this 3 micrometer feature due to water. And then the lunar, and that's provided by JPL, and then the lunar thermal mapper from the University of Oxford that has 15 channels for temperature and composition, again at sub 100 meter per pixel resolutions to get at the temperature of the surface. Now, where are we in our timeline? Well, I am thrilled to say that in spite of a global pandemic, I have a team that perseveres, that communicates well, and we are on track, on schedule, in spite of that. And so a huge thank you to our team in figuring out ways to work together. We have just passed the milestone of our critical design review, and so are now onward to fabrication. Bits of hardware are arriving all the time, and it's really quite exciting that in 15 months, we will have our flight system assembled. So at the moment, NASA has manifested Lunar Trailblazer on IMAP, which launches in 2025. There's a lot going on at the moon beforehand, and NASA has been considering earlier launch options. But when we launch as part of our ESPA rideshare, we will then travel 5 to 8 months to the moon, after which we will embark on our 1-year science mission for mapping the form, abundance, and distribution of water. How do we do that? Well, it's these nested data sets from our two instruments. So we have simultaneously acquired an hyperspectral image cube and a multispectral thermal mapper cube. So for each pixel, we get a spectrum of the form of water and of the absorption band depth that allows us to calculate the abundance, determine whether it's ice or adsorbed water, and then simultaneously nested in those pixels, we get the temperature. So this is really the key to our mission, is those simultaneous quantities, and we get those in targeted spots around the moon. Here you can see the target density for the permanently shadowed regions along an exemplary Lunar Trailblazer ground track. So there are 4 goals, but the way to think about them is there are objectives related to water on the sunlit moon, form, abundance, distribution, and then importantly for science, how it varies as a function of latitude, soil maturity, lithology, and time on the sunlit moon. And then for the shadowed moon, where is the ice? How much is there, and which places are full of ice and which are empty, and why? And so that's tracing ice abundance and temperature. And then along the way, we get some awesome compositional data for those of you interested in lunar crustal evolution. So I'll take the remainder of my time to talk about the top five, basically advancements that we expect Lunar Trailblazer to provide. The first is the form of water on the moon. So especially on the sunlit side associated with these micro cold traps, there's really this question of, is it ice or is it loosely bound water? You can see here as we transition from blue to gray, how Lunar Trailblazer in its HVM cubed instrument adds the additional spectral channels to fully capture that 3 micrometer feature to distinguish the form and abundance of water. Next, the question is, why is the water more enriched in some areas and at some times than others? So we'll be targeting some of these locales where water enrichments have been reported. We'll be looking at 3 times a day for several of our targets to assess change as a function of morning, afternoon, evening. Where is the water changing with time? And then we'll be looking as a function of latitude. And all of this is important because temperature matters. And those of you who are savvy to this know that as we look at this 3 micrometer feature, it's influenced by what's going on at the longer wavelengths. As we move into daytime lunar temperatures, you can see that shape is changing, making Lunar Trailblazer's simultaneous composition and temperature data with its 2 instruments all the more important. I think for the plans that David Parker and Jim Green talked about, among our most important data are those we'll get at the poles from the permanently shadowed regions. In orange, you can see exemplary our 2 footprint sizes superimposed on Cabeus crater. Within those footprints, we'll be getting at where is there water on the surface to sub 100 meter per pixel levels to 500 meter per pixel levels, depending on the light level. This is very important for the question of which of the cold traps actually host liquid water, how much, where exactly, because this is where we'll guide our future rovers and landers. You heard Jim allude to this question. The other question is, how pure is that ice? Is it like the organics, the cold traps on Mercury, which of course are very rich repositories of organics delivered to the inner solar system? We don't know right now, and Lunar Trailblazer will provide the spectral data in this key wavelength range to answer it. And then finally, the other set of discoveries I expect our mission will make is regarding the silicate composition of the moon, crustal evolution, the history of volcanism. We have potentially ultramafic rocks. We certainly have high silica units. We don't know quite how these relate to volatile content and evolution. And one of the key aspects of Lunar Trailblazer is we'll get compositional data that allow us to distinguish some of these more extreme lithologies that Diviner discovered on the moon. So with that, I'll wrap it up and say that our focused science investigation is really geared toward identifying the best exploration sites on the moon for future landed reconnaissance and answering fundamental questions about the lunar water cycle. We're on schedule, on track for an October 2022 delivery of our flight system, at which point we can start collecting data to support all of the future lunar missions. Thank you.
Fantastic. Professor Ehlmann, thank you so much. This is such an amazing mission. And as a former mission person myself, I just can't imagine the leadership challenges in dealing with getting all the hardware delivered on time, finishing the design process, et cetera, and on top of a pandemic. So what an amazing job, and thanks for your leadership on this. The community is going to be very excited and grateful when this gets orbiting and gets its results. So what an exciting mission. Thank you.